So welcome to week 3 now of our course, and the theme for the week is ethereal problems and solutions. We'll get to the quotes of the week in just a second or two, but here are the main topics we'll be looking at. We'll be starting off with Einstein's starting point, the two postulates that he enunciated in his special theory of relativity, the June 1905 paper. And essentially what he said is, we're going to just take these two things for granted. They actually were two principles that were well established in physics, but that seemed to be somewhat in contradiction with each other. And what Einstein did is sort of had an intellectual breakthrough, because he saw that actually, even though they seem to be in contradiction with each other, that if you took both of them to be true and then worked out some of the implications, it gave you some very interesting results. So he was just basing this on these two postulates, so we'll figure out what those postulates actually are. I'll just give you a heads up. One of them is the so-called principle of relativity, and the second one is what he called the principle of light constancy. And because that second principle deals with light and whatever light constancy means, we need to figure out more this week about how light waves work, how waves in general work, some of the key principles of light waves and the phenomena of light waves, so that we can understand the background to what Einstein is working with here. So we'll spend a little time exploring some light waves, more or less in a qualitative sense, not a quantitative sense. We won't do a full physical review, say, of how you describe light waves mathematically and so on and so forth. And then we'll talk about something called the ether. You see, ethereal problems and solutions. That's where it comes from. And there was a real problem with the ether. It was cutting-edge physics at the time. A number of very good and great physicists had been working on it. Whatever it happens to be, it's really the idea of the medium for light waves. So sometimes it's called the luminiferous ether, a light-bearing ether. It's we assume that waves must travel through something. Water waves travel through water, sound waves travel through air or whatever gas is involved, and therefore light waves must have a medium which they travel through, that the vibrations, the light vibrations, the electromagnetic vibrations that make up light, there must be some medium involved, and so that was known as the ether. And yet there were some key problems with it that Einstein was really worried about and bothered him greatly. And not only that, there were certain experiments that bothered everybody greatly, actually. And the classic one is known as the Michelson-Morley experiment. So we're actually going to spend a fair amount of time looking at this in a mathematical sense. Not deep mathematics. It'll mainly be algebra that we're using here, but this will be our first foray where we get a little more quantitative than we have been up to this point. But don't worry, we'll take our principle of festina lente, make haste slowly, so we won't try to rush through it, but make sure we're laying that solid foundation as we construct our mental models of what this special theory of relativity is all about and the implications thereof. So the Michelson-Morley experiment will directly relate to what the ether is like and give a certain result. And then another well-known experimental result called stellar aberration also relates to the ether, and we'll find out that these two are actually in contradiction with each other. So you had two very well-known experimental results, and as they related to the ether, one said one thing, the other said the other thing, and it really puzzled the physicists of the day. So we're talking about, this was in the 1880s, essentially. Stellar aberration actually went all the way back into the early 1700s, around 1725 or so it was first observed. So the question was, what do you do with something like this? How do you solve a problem like the ether? It seemed like they needed the ether. Otherwise, what is waving in terms of a light wave? And the properties of the ether, the Michelson-Morley experiment was saying one thing, and stellar aberration was saying another thing, and there are other experiments too, sort of on one side or the other. And it was a real problem in the 1890s and up to 1905. And so then we'll look at some of the solutions to this. How do you solve a problem like the ether? For those of you who maybe remember the musical The Sound of Music, sort of comes from How Do You Solve a Problem Like Maria. So now that I've said that, you can probably, for those of you who remember the musical, can't get that out of your head, so I apologize for that. But in this case, it's How Do You Solve a Problem like the either? Well, there were certain solutions. Some of them somewhat ad hoc solutions, just sort of pasted in there and see if we can get our theory to work with it. Einstein's solution was much more elegant and simple, and so we'll certainly want to find out more about that. So that's where we're going this week. And let's go back to the quotes of the week. Have them on your handout. First one is, there's no doubt that the special theory of relativity, if we look at its development in retrospect, again, this is by Einstein, was ripe for discovery in 1905. And so we will see some of that as we talk about some of these things, that other people working in this area, that it definitely was a well-known problem. They had somewhat solved it, but not in a very satisfactory way. And so Einstein came along and took a very different approach and came up with a similar solution, actually, to what others were getting, but in a more satisfying way. But even having said that, it still took several years, a number of years, before people really accepted Einstein's approach to the problem versus some of the other approaches there. In fact, Einstein's approach was almost too simple. It seemed too simplistic, that he was just assuming these two postulates and then taking off from there, when some of the other theories that were getting similar results were much deeper, much more sophisticated in terms of their physical and mathematical methods, and so on and so forth with that. So, but certainly he said that if he hadn't done what he did in 1905, somebody else probably would have done it in the next few years. It was in the air, as it were. As an aside, actually, for his general theory of relativity, not the topic of this course, but 10 years later, that probably would not have been done as early as it was if it hadn't been for Einstein working on that. Second quote, I lived in solitude in the country and noticed how the monotony of a quiet life stimulates the creative mind. I put that in here just, not that we should all maybe go live in the country in monotony or live wherever in monotony, but in our technologically oriented society where we're always hooked in and connected and so on and so forth, sometimes we need to unplug, as it were. Turn off the email, turn off the internet, turn off the texting, turn off the phone, the iPod, whatever it happens to be, and use that time to do some thinking, because that's what topics like this really require. They require some deep reflection on various matters, and that's what Einstein in particular was very good at in terms of his powers of concentration and stimulate that creativity and innovative thinking and deeper understanding of things. So if you can use that as inspiration, Einstein's quote there, inspiration for doing that, sometimes you'll probably be better off, at least in terms of understanding whatever you're trying to understand. Then he also said, when I am judging a theory, I ask myself whether, if I were God, I would have arranged the world that way. And then the second quote, very famous quote, subtle is the Lord, but malicious he is not. And I ask you just to consider what that might mean, even without understanding Einstein's own context of how he came up with that, what that might mean. Clearly, the whole topic of Einstein and religion is a huge one. There have been books written on his ideas in this area, quotes all over the internet again on these topics. Famous one besides the subtle is the Lord one. Another famous one is that science without religion is lame, while religion without science is blind. And sometimes when you pull these quotes out of context, it's you can get a misunderstanding of what Einstein's beliefs in the area were. He really believed in more of you could almost say a cosmic God or a cosmic religion, certainly not a personal God. And you have to say also in this respect, Einstein was definitely not a theologian. It's not that his ideas were naive in a sense, but that he hadn't, the sophistication of his ideas was not necessarily as deep as it might have been if he'd spent the same amount of time thinking about these matters as he did with his physics and his science. So whether it's Einstein or anybody else, you have to take those things into consideration when they're sort of pronouncing on fields outside their own. They might have very great wisdom in that area and very great insight, but we can't just assume because they're an expert and sort of a person everybody looks up to in one area, even a genius, doesn't mean that goes over into another area. So when he talks about when I'm judging a theory, I ask myself whether if I were God, I would arrange the world that way. He really believed in the beauty and grandeur of physical reality. And his religious belief, in a sense, if you could call it that, was that we humans could actually gain insight into that through our reason and through our rationality and through mathematics as well. And that's what he is referring to when he also says things like, subtle is the Lord, but malicious he is not. That the way that the universe is constructed, the marvelous structure of reality, we actually can penetrate into the insights of that and the grandeur and beauty, as he put it in other places as well. So just some quotes of the week to ponder there if you want. And then, again, this week we'll be looking at Einstein's starting point, the two postulates, and then especially light waves and the problem of the ether. Spend some time with the Michelson-Morley experiment and stellar aberration, and then sort of see the solution, Einstein solutions, as well as some of the other solutions to this problem, like the ether. And then next week after that, we'll really start to get into the weird and strange results that come out of Einstein's two postulates when you accept both of them to be true. Okay, so now we come to Einstein's starting point, the two postulates. In other words, we come now to the famous June 1905 paper entitled On the Electrodynamics of Moving Bodies. And this is the paper where he introduced his special theory of relativity. And sometimes we get the idea that, again, he was 26 years old, he was a clerk at the Swiss Patent Office. This came out of nowhere. But if you actually look at it, he had been working in this area, thinking more and more deeply about these things for 8 to 10 years at least. We see this in some of his correspondence, and unfortunately we don't have any notebooks from that time period where he was working on this. We do have some of his school papers and things like that, school notebooks, but nothing specifically on this. But he does mention it several times in his correspondence with friends and with his girlfriend Mileva, and then later his wife. And so we know he was thinking about this for a number of years. And in fact, later on he described it as this psychic tension he felt, that this was an area, whatever, and we'll get to sort of what this means here in a minute. This was an area where he saw certain what he called theoretical asymmetries, and he could not figure out, so sort of contradictions. He could not figure out what was going on and what was going wrong. He just felt there was something wrong there and actually couldn't see it until a few weeks before this, in April 1905, he went for a walk with one of his friends at the patent office, Michael Besso. Einstein had actually helped Besso get a position at the patent office the year before or so. They'd been friends before that and often went for walk and talks, as it were, during lunch hour or whenever, and they discussed physics. And one of the things evidently they discussed was this. And so one day he came back and he told Besso, "I've solved it." And the famous phrase he later said was that time is suspect. In other words, the normal notions of time that physicists and pretty much everybody had for years and years and years, something was wrong with them. That's where the contradiction lay, or the solution to the contradiction that he felt. So we need to sort of figure out what's going on with that. What are these two postulates? What's going on on the electrodynamics of moving bodies? And also note that Einstein was not the only person working on this. In fact, there were some very well-known, respected physicists working on it, such as Hendrik Lorentz, and André Poincaré. In fact, two of the leading physicists of the time, Lorentz in the 1890s had extended Maxwell's theory of electromagnetism in a number of different directions, expanded it, and then Poincaré and Lorentz worked together to a certain extent in the years right before 1905 to put it into very sophisticated mathematical formalism. And it was a very detailed theory. So again, it wasn't like Einstein just came out of nowhere and no one was working on this and he had these great insights, but that other people work on it. And in fact, Lorentz and Poincaré came up with some of the same ideas that Einstein did in terms of his theory of special relativity, but from a totally different direction. And actually a much more complicated way of deriving it. And Einstein's way, his approach to the matter, was much simpler. In fact, it was so simple in some respects, people dismissed it just because of its simplicity, and they sort of preferred the more sophisticated, complicated theories of Lorentz and Poincaré. So in fact, it's a benefit for us, though, because the basic concepts and math involved in Einstein's theory are such that we can actually teach it in a course like this and understand it, even if we don't have that more sophisticated mathematical background. So, what was actually in this paper? What's this idea with electrodynamics of moving bodies? I hope you, especially those of you who are doing the quantitative approach, that you read the paper. Again, I don't expect you to understand it. Sometimes you hear it said that anyone should be able to sit down and understand this, sort of if you have a college-level education or something like that. I don't think that's true. There are a fair number of equations in it. There's a fair amount of assumed knowledge about physics and math and so on and so forth that you really need to get an understanding of it. But for our purposes, even if you're doing the qualitative approach, it's good just to skim through it, look at the various section titles, see how he organizes things, read the introduction, read some of the conclusions, and get a sense that way. So electrodynamics of moving bodies deals with electromagnetism here. Dynamics refers to forces, so we're talking about sort of electrical forces involved in moving bodies, just objects moving like that. So what was Einstein's approach? Well, it was very different from the approach of people like Lorentz and Poincaré, who were trying to build very detailed models of things like electrons and the so-called ether, which is the medium or seat of electromagnetic forces, and light waves and things like that, of which we will talk more later. Einstein, if you look at his paper, he starts off with, first of all, just a statement of some things that were bothering him, these so-called theoretical asymmetries. And one of the big ones was simply, if you take a bar magnet, so say we've got a bar magnet north and south, and then you have a coil of wire here. So here's our magnet. Here's the wire. And today we'd say there are electrons in the wire, so there are charges there that could move around the wire if we attach it up to a battery or something like that. But also, from Maxwell's theory of electromagnetism, that if the magnet moves towards this coil of wire, we know the magnet generates a magnetic field around it in some sense. If that magnet moves toward that coil of wire, the theory said that it would generate an electric field in the wire, in and around the wire, and therefore the charges in the wire under the influence of that electric field would start moving. In other words, more technically what happened is, as the magnet moves here, the magnetic field in the vicinity of the wire is changing, and that generates the electric field, which then pushes the charges around the wire. In other words, you get a current in the wire. Okay, so Einstein says, great, that's fine. But that's if the magnet is moving. If you say, let's consider a different case, let's keep the magnet stationary and have the wire move toward the magnet. Okay? You get the same result. The physical situation is the same. One is moving toward the other. You get the current in the wire. But the theory in that case gave a very different explanation. It said in that case, as the wire moves toward the magnet, and there's a magnetic field around the magnet here, that magnetic field acts directly on the charges in the wire, which are actually moving toward the magnet, the whole thing, obviously the charges in the wire are constrained to move in the wire, so the whole thing is moving toward the magnet. And the theory said if you have a moving charge in a magnetic field, there's a force on it, so it starts, again, circulating around like a current. So physics, for our purposes, is useful there to understand, but the most important thing is physicists were giving two different explanations for the same thing. And in this case here, they're saying it's the magnetic field that actually is pushing the charges around the wire. If the magnet, though, is moving, it's an electric field that's generated that pushes the charges around the wire. And Einstein found this rather bothersome. He did not like it at all. He felt there should be one physical explanation, because it really shouldn't matter whether the wire is moving, the coil of wire is moving toward the magnet, or the magnet is moving toward the coil of wire. So that's one of the theoretical asymmetries he highlights at the very beginning of his paper, his June 1905 paper. And by the way, I can't remember if I mentioned this or not, but he had his conversation with Besso in mid-April or so, 1905. Within 6 weeks, he'd publish the paper, or finish the paper and set it off for publication. So again, you see that he had been mulling these things over for a long time. They've been percolating in his mind, in a sense. And so once he got the key insight, it didn't take him long to work out some of the key implications. So if you look at the actual paper, it's divided into two key parts. And the first part, he labels a kinematical part. And then the second part, actually, which we'll write up here, it's an electrodynamic part. Okay, where he takes some of the results from the first part and applies it to Maxwell's theory and a few other things in terms of the theory of electromagnetism. We're not going to go into the details of that, because the key things for us, these two postulates in particular, really come from the first part here. Kinematical part, what does that mean? Well, kinematics just really deals with things in motion. It doesn't worry about forces and things like that, so it's not worrying about this dynamic stuff here. It's just saying, let's go back almost to first principles. And let's make sure we really understand how we measure things in motion, velocity and length and time. So very simple beginning, and that's, again, one reason why Einstein's approach to it was dismissed to a certain extent, because it seemed like it was just almost trivial stuff he was trying to do. So this kinematical part here, what was he doing? What were these two postulates? Well, the first postulate was the principle of relativity. And this postulate goes all the way back to Galileo in the 1600s, if in other forms, perhaps even before that. But certainly Galileo put it into its most famous form that influenced later thinkers such as Isaac Newton. And essentially, the basic idea is, for Galileo, he imagined ships on the ocean. If you have two ships on the ocean and the water is fairly calm, air is fairly calm, but they're in motion with respect to each other, if you're on one ship, the question is, are you moving or the other ship is moving? In our day, maybe cars or trains. If you've been on a train before, another train is right next to you, you see all of a sudden things are moving if you're stationary at first, and then you're not sure, is your train moving or is the other train moving as you look out the window? So the principle of relativity says that motion is relative, that there's no absolute, term we'll use later on, absolute frame of reference. And we'll explain that in more detail later on. But there's no way you can really tell that you're moving versus something else is moving unless you specify it. You can say, okay, compared to the floor here, I'm moving or not moving. But of course, I could think, well, the floor is attached to the surface of the earth, and the surface of the earth is moving. So in that case, with respect to the center of the earth, the whole floor, and me and everything else, all of us, are going around the center of the earth. So that the principle of relativity says that if you really think about it, you can't tell whether you're moving or not. You can say, with respect to this or that, I'm moving, but then maybe that person over there, I could say they're moving, but they might say, no, I actually see you moving. more specifically, and this was the thought experiment we did early, the first thought experiment in week 1. If you're in a railroad car and you have those various items in there, and to see if you can actually do an experiment or put them together in some way to tell whether you're moving or not. And so a more precise version of the principle of relativity is to say that there's no experiment you can do in a situation like that that will tell you whether you're moving or not. And another way to say this, there is no state of absolute rest. You can't define any frame of reference that you can say is absolute rest to everything else, and then you refer any given motion to that state of absolute rest. So, principle of relativity, this was well established in physics. It wasn't anything that new. But Einstein said, okay, let's take that. But then he also said there's a second principle coming out of electromagnetism and relates somewhat to the bar magnet and coil example I gave in a minute. So he said electromagnetic theory, we now know, says a few different things. It basically seems to violate the principle of relativity. Again, the coil and magnet, it shouldn't make any difference whether the magnet's moving or the coil is moving. And in actual fact, experimentally, it doesn't. You still get the same current around the coil, and yet physicists were explaining the two situations in two different ways. And so Einstein said, if we really believe in the principle of relativity for everything, then that shouldn't be so. And so that was one thing, the coil and the magnet, but also electromagnetic theory said that light was a wave. And that also led to things where it seemed the principle of relativity was not valid for electromagnetic theory. In particular, and next week we're going to, or I should say this week, we're going to explore it more in some of the video clips. What did it mean that light was a wave? This came out of James Clerk Maxwell's electromagnetic theory, showing that there were electromagnetic waves and vibrations that traveled along through the so-called ether, which was the medium through which light traveled. Waves have a medium. Water waves travel in water. Sound waves travel through the air. Light must have some sort of medium through which the electromagnetic disturbance travels that makes up light, and that was typically called the ether. Now, the idea of the ether goes way back centuries, actually, but at the time of the late 1800s, early 1900s, the idea of what was known as, we'll use the full term here, the luminiferous ether was the idea of a medium that was everywhere. Okay, because it had to be. Anywhere you can have light, even in a vacuum. You can send light through a vacuum, and therefore there had to be a medium that carried those light vibrations, as it were, those electromagnetic vibrations that made up light waves. And this ether, if you think about it, was had very interesting properties because on the one hand, you can just move your arms around and things like this, and everything's seems to flow right through it. There's no drag or friction that we can tell of. And yet, on the other hand, physicists knew that for a wave-like phenomenon, if you have very high-frequency vibrations, and light actually is a very high-frequency vibration compared to most anything else, that only occurred when you have really stiff, rigid type of materials. Think of like a really stiff, rigid metal bar versus something a little more pliable in terms of if you bong it with something, the type of vibrations you will get. So the ether, on the one hand, seemed like it should be very stiff and rigid so that it could generate or carry those electromagnetic waves that were light. And yet, on the other hand, it seems like things can just pass right through it. So there were a lot of mysteries about the ether, and that's what people like Lorentz and Poincaré had really been working on for the last 15 years or so when Einstein came along in 1905. So how is this a problem, though, for the principle of relativity? Well, if the ether exists, and it's really like the background of the universe, really, that everything sort of sits in the ether is all around us, then that could act as an absolute frame of reference. I could say, am I moving or not? Well, if I can just measure my motion with respect to the ether, I could tell, hey, I'm moving. In other words, the ether would be an absolute frame of reference, a frame of absolute rest, and all motion then could be referred to this supposed ether. And that would go against the principle of relativity. And more specifically, in terms of what Einstein was doing with his two postulates here, he had the principle of relativity. The second postulate that he stated, second principle, going along with this, just to be precise, was what he called the principle of light constancy. The principle of light constancy. And what he suddenly realized was, because it seemed like these two things were in contradiction with each other. The principle of light constancy, which we'll explain as we go along this week, get into that a little bit more, really is a statement of the fact that light is a wave and the so-called luminiferous ether should exist. This light-bearing, luminiferous being light-bearing ether should exist. And yet that seemed to go against the principle of relativity, another well-established principle. So you had two very well-established principles in physics that seemed to be in contradiction with each other. And that was what really bothered Einstein. And so what we need to start figuring out this week and beyond, is exactly what does this mean here, this principle of light constancy, and how does it fit together with the principle of relativity, or how it doesn't fit together with that, and then how Einstein put the two together and said, actually, they're not in contradiction with each other. But if you assume they're both true and you work out some of the implications, you start to get some very weird results. And these are the results that you see actually in the kinematical part of his paper on the electrodynamics of moving bodies, where things like length and time aren't defined as we would normally think them, in the sense that they're not absolute. They're relative, the relativity of lengths and times. Simultaneity and clock synchronization becomes problematic. And in fact, another point here, if you read this, note the examples he uses. He talks about trains and clock synchronization. These were not just philosophical notions or problems that he's working with. In the patent office, this was cutting-edge technology in terms of synchronizing train schedules, synchronizing clocks between different stations, and so on and so forth. There's no direct connection that we can point to between his work at the patent office and some of his ideas. Unfortunately, all his patent work was destroyed after about 14 years, I think it was. That was just the normal procedure, that they'd keep the records for 14 years and then get rid of them. And so we don't actually have really any of the patent applications Einstein worked on, but we do know the types of patents that were going through the patent office all the time. And a lot of it dealt with issues of clock simultaneity, clock synchronization, trains, and so on and so forth. And so it's interesting and important that Einstein is using some of those examples in this paper. So again, the overall context of what he's working with, not only the context of physics and the key problems of the day that people are working on, but also the technological context in which Einstein was embedded, in a sense, in the Swiss Patent Office. So as we move ahead here, our goal will be to learn more about this principle of light constancy and a little bit more about waves, so we can understand this and then see how that relates back to the principle of relativity, and how when you put it all together, you start getting some very weird results.